So where we got to yesterday was that we had reduced the horrible partial differential equation in 6 variables, which is posed by the time-independent Schrödinger equation for a hydrogen-like ion, to this equation here. Sorry, not being premature. To this. So the internal motion had been separated from the translational motion of the atom as a whole, and we had exploited by using a change of variables for center of mass coordinates and the separation variable, and we had used the work that we did with the angular momentum operator earlier on to show that we could express the internal Hamiltonian in this format here. Sorry, this was called R, I think. That's right, for the internal motion. Right, and then I pointed out that this Hamiltonian commuted with the angular momentum operators, because the only mention of the angles theta and phi sits inside this total angular momentum operator, and therefore we can seek stationary states. There's going to be a complete set of stationary states which are simultaneous eigenfunctions of E and L, right? So we will also have the statement that L squared on E and L is equal to L plus 1, E and L. And then when we're using these stationary states, the action of this operating will be replaced by this eigenvalue, and now we do end up with what I wrote originally, which is that we're going to have a Hamiltonian which has a subscript L, meaning it's the one that's valid for stationary states which have total angular momentum quantum number L, which is going to be PR squared over 2 mu plus L plus 1 h bar squared over 2 mu r squared minus ze squared over 4 pi epsilon naught r. And this is fundamentally a Hamiltonian analogous. This is a Hamiltonian analogous to that for the harmonic oscillator, in the sense that we have now only one surviving coordinate. Of our 6 coordinates, we're down to 1. That's this here, the modulus of the separation vector, and its conjugate momentum PR. So we've made an enormous simplification, made tremendous progress. And we're going to knock this into submission using the same approach as we did with the harmonic oscillator. We're going to define what will turn out to be a ladder operator, AL, which is going to be defined to be dimensionless. It's going to be A0 over root 2. I better write this down from notes rather than my memory, because these factors do matter. I PR over H bar minus L plus 1 over R plus Z over L plus 1 A0, where A0 is the following not very helpful item: 4 pi epsilon naught h bar squared over mu E squared. So this is an object. I'll make it convincing. Well, let's make it convincing now. What is this object? This is the so-called Bohr radius. So it was introduced by Niels Bohr before there was proper quantum mechanics, using what turns out to be a fallacious model of hydrogen, the Bohr atom. And the way to see what its dimensions are actually to bring this up onto this side and say, look, this is going to be E squared over 4 pi epsilon naught A naught. Now on this side, A naught's on the top, not the bottom, so therefore I have to say this is equal to H bar over A naught squared over mu. So out of this equation, by putting that E on the top and this 4 pi epsilon naught on the bottom, dividing through by A naught squared to get this on the bottom, so that this is something we understand to be, this is obviously electrostatic energy. And what's this that we see on the right side? Well, h bar k is momentum, right? So this is more or less p squared over mass. This is the reduced mass. Recall, this is the reduced mass, more or less the mass of an electron. So what we have on the right-hand side is p squared, well, it is p squared for k is equal to 1 over a naught. So if you have a wave which has a wavelength which is comparable to 1 over this scale radius here, sorry, a wavelength comparable to this scale radius here, not worrying about 2 pi's at the moment, then what you have on the right here is, so this side is 2 times kinetic energy associated with a particle which has a wavelength which is on the order of A0. And what we have on the left side here is the electric energy. So the scale that's being set, this dimensional quantity, the Bohr radius, is the natural scale at which the kinetic energy associated with the uncertainty principle, the 0 point in it, what in the harmonic oscillator we would have called the 0 point motion, is on the order of the electrostatic energy. That's dimensionally where this number comes from. That number comes from. So, with the thing to notice now is that AL is dimensionless. Why is it dimensionless? Well, this cancels the dimensions of this. Obviously, this cancels this. This is all dimensionless, this factor, apart from the A0. And here we're looking at, again, this is PR divided by, with this put on the bottom, h bar over A0, therefore h bar k, therefore something with the dimensions of p. So this thing here, this operator here, is dimensionless. Same as the ladder operators in the harmonic oscillator were dimensionless. Okay, so what do we do with that? What we do is we calculate what A, and this thing, of course, carries the subscript little l because little l, the orbital quantum number, is appearing in its definition. And what we do is we now calculate AL dagger AL. Right. So what does this give us? We have obviously an A0 squared over 2 out front because we're going to have 2 A0s and root 2s. And then we're going to have PR we showed was a Hermitian. We engineered that it was a Hermitian operator. So when I take the Hermitian adjoint of what I have up there, I get a minus I PR. The minus sign is from the I over h bar. And then the rest, of course, is the same because it's Hermitian. Well, it's just boring numbers. Plus Z. Well, actually, this is an operator, strictly speaking, but we're in the position representation. So it looks like a number. And that has to be multiplied onto IPR over h bar. So no minus sign, because this is AL I'm writing down now, minus L plus 1 over R plus Z over L plus 1 A0. So we have to multiply this stuff out. And the way we do it is we regard this in the back here as one factor and that in the front as another factor. So this is looking like the product of a number minus some number, a number plus some number, right? It's the usual pattern. Just so this is mirroring very closely what we did with the harmonic oscillator. So we get A0 squared over 2. These two obviously multiply together, and we get PR squared over h bar squared. And then these I have to multiply together. So what do we get? We get the square, basically, of this number of this number here. So we have plus L plus 1 over R squared plus Z over L plus 1 A0 squared minus the cross term here, which is going to be, well, there'll be minus twice, 2Z. Those are going to cancel, and we will have A0R. So that's the two easy parts, right? Because it's the front thing squared plus the back thing squared. And now we have to think about the cross terms, which would vanish because this is A plus B into A minus B, spiritually. These cross terms would vanish if we weren't dealing with operators, and they fail to vanish only because we are dealing with operators, so that there's a failure of commutation. In other words, the PR, well, okay, so PR commutes with this, so for the cross terms, we don't get anything from this thing on this, but we do get something from this thing on this, namely we get the relevant commutator. So the extra term that arises because we're working with operators is going to be I over h bar. That's that. So this minus sign and this minus sign cancel. We have that L plus 1, and then I have a PR, comma, 1 over R, close big bracket. That's what I'm going to get from this term on this term, not cancelling on this term on this term. Okay. So that's going. So what is this going to come to? Well, let's rearrange things. A0 squared over 2, PR squared over h bar squared, plus L plus 1 squared over R squared, minus, I'm going to put this one down next, 2Z over A0R, then this term plus Z squared over L plus 1 squared A0 squared. And when I have to do this, what I remember is something we handled already last term, that when I had to do, it arose when I was doing, when we were doing the commutator of P and V, the potential function of X, that turned out to be the rate of dV by dx times the commutator of P and X. This is exactly the situation we have here because this is the operator canonically conjugate to R. So what we have here is the derivative of 1 over R, which is so minus I L plus 1 over h bar times minus 1 over R squared, because that's the derivative of 1 over R, times PR comma R. But this is a piece of a canonical commutation relation. This is equal to minus IH bar, right? We showed that R comma PR is equal to IH bar. So in this order, it's minus IH bar. So we have rather a load of minus signs. Let me see. I think we have 1, 2, 3 minus signs and another minus sign coming from here. So I think in total we have a plus sign. So this stuff here, I believe, comes to L plus 1 over h bar R squared. Sorry, the h bar cancels. This h bar is on top, that's on the bottom. So we get an L plus 1 over R squared. And this can now be combined with this, except I've got the wrong blinking sign. Let me just double check that. Yep, I'm looking for minus. Is it minus? Well, anyway, I want it to be minus, so let's declare it to be minus. And I'm sure it is minus. I'm sure it is minus. Let's not spend time chasing down some wretched sign, because now what we're going to do is combine this. So let's do this little side calculation here. We're going to have L plus 1 over R squared, brackets L plus 1 from up here. That's the L plus 1 squared minus 1 times this stuff. So you can see we're going to put this, and this is going to give me an L plus 1, which is exactly what I want. So this is going to be A0 squared over 2 PR squared over h bar squared plus L plus 1 over R squared minus 2Z over A0R, close brackets, and then I'm going to take this and join it on that, so we get plus garbage, and the garbage term is Z squared over 2L plus 1 squared. And this should all be dimensionless. I think it probably is dimensionless on the grounds that it's the product of two dimensionless operators. Now, what's the point of this ridiculous exercise? The point is that we should see the original Hamiltonian peeking out here. We should basically have our original Hamiltonian plus garbage. So the in order to get our original Hamiltonian, we need to have a mu under here and a mu under here. So why don't we multiply by a mu on the top and the bottom? So this is a naught squared mu. And we want to take this h bar outside. And then that won't be under there as we want. We can allow that 2 to wander inside. And then this bracket becomes HL. This stuff here becomes HL. And we've still got unwanted garbage in the back. But that's exactly how it worked with the harmonic oscillator. Remember, A dagger A was equal to H, the Hamiltonian, over H bar omega minus a half. There was garbage in the back, which in that case was a half. So this is obviously some constant with the dimensions of energy. I better make sure that I've done that right. It's the h bar should be squared. Yes, of course it should, because it was the h bar I took out from there. Otherwise, it is correct. And that's just the business. So we've expressed h. Let's write this down in the other way. We've said that h is equal to h bar squared over a naught squared mu, which must provide the dimensions of energy, a dagger L A L minus z squared over 2 L plus 1 squared. Another way of writing it. We've expressed h basically as dimensionless constant times a sort of a dagger A. So this is the harmonic oscillator trick, and it's all just looking a little bit messier. But this is only a boring number, right? It's just, I mean, what's the difference between a half and this? It's just a number. They're both just numbers, rational numbers. Okay, so what do we do next? What do we do in the harmonic oscillator? We calculated a dagger comma a. We found the commutator. That was the next thing that we did, and that's what we do just right now. Make sure I'm done it the right way. No, it's more convenient to work it out the other way around. Later use. All right, so what is that? We have to write this horrible thing down again. So we're going to have an a naught squared over 2. Open a square bracket because we're talking commutators now. Write down I PR on h bar, because I'm writing down a now, which is just there. I need to write down minus L plus 1 over R. I don't need to write down the boring constant in the back, the Z over L plus 1 A0. That will commute with everything in sight, and therefore will make no contribution to the commutator. Then I have to write down the corresponding parts of A dagger, which is minus I PR over H bar minus L plus 1 over R, and now I can rest easy. So this is what the commutator that I have to do. Obviously, so PR commutes with itself, nothing doing there. PR, on the other hand, does not commute with this, so we are going to get A0 squared over 2, I L plus 1, that's that L plus 1, over H bar, that's that H bar, PR, comma, 1 over R, commutator. I get that from that, or at least live in hope that I do. What did I do with the minus sign? I put it in the bin. I shouldn't have done, right? There should be a leading minus sign. Then I have the same term, actually, because here I'm going to get plus, but everything, plus this, except I'm going to have a 1 over R, comma, PR, which, of course, is minus this. So I'm going to get this all over again, so why don't you just rub out the 2, and then it's right. What's this commutator? We've already discussed that problem. It's going to be, the rate of change is going to be d by dr of this times the commutator. So this is equal to minus A0 squared I L plus 1 over H bar. And then I'm going to have a minus 1 over R squared for the derivative of this times PR, comma R, commutator, because that's how these things work. But this, once again, is minus IH bar. So the two minuses here cancel. The two i's make another minus sign, which kills this minus sign. All being well, this is equal to A0 squared L plus 1. The H bars cancel over R squared. check sign. Yeah. Should have a... No, that's correct. That's correct. Good. All right. So and we want to express this. Remember the commutator. So in the harmonic oscillator case, what was this commutator? This commutator was actually 1. So the bad news is it's not looking very promising. At this point, you think, oh, no, it's not good because our commutator is some damn function of R. But we've seen that damn function of R somewhere before, up in the Hamiltonian, basically. I've lost the Hamiltonian. There it is. So we've got L plus 1 h bar squared over 2 mu R squared is appearing in the Hamiltonian. So supposing I would take h L plus 1, and from it I would take HL. Then everything in the Hamiltonians would cancel except that middle term, which has the right form. Namely, it contains a 1 over R squared. And what would we have? We'd have h bar squared over 2 mu, I think, R squared, brackets L plus 1, L plus 2, minus L plus 1. Did I do that right? Live in hope. Okay, so obviously there's going to be a factor of L plus 1 common, and then we're looking at the difference between L plus 2 and L, in other words, 2. The 2 is going to cancel this, and this is going to equal L plus 1 h bar squared over mu R squared. So we can express, with this little side calculation, we can go back up the board and express this as an appropriate multiple of the differences in the Hamiltonians. There's going to be a naught squared, that's this a naught squared. Then we will want to multiply by mu, divide by h bar squared, and then we'll be able to say this is HL plus 1 minus HL. Check that we haven't got any horrible factors amiss. Okay. All right, what was the next thing we did in the harmonic oscillator? Having got the commutator of the A and the A dagger, and having expressed H as a product of A and A dagger, the next thing we did was calculate the commutator, use these results to calculate the commutator of A with H. So that's what we do now. I will do it here so that we can see our results. So I want to calculate the commutator AL, HL. And I can do that by expressing this HL. You see, HL is basically a product of the A's. Now, I've only got to locate the wretched product. It's at the top there, isn't it? It's so hard from this position to see what you need to see. This product, et cetera, et cetera, et cetera. There's a statement. This is the statement I'm looking for. I want that statement, all right? So this HL can be traded in for that product. So we have h bar squared over A0 squared mu times the commutator of AL and AL dagger AL. And I can rest easy there. I no need to put this stuff inside a commutator because it commutes with everything in sight, so it can't contribute to the commutator. So this is the commutator I have to evaluate, and this is easy peasy because this is the commutator of a product, some A with B and C, which in principle is the commutator of A with B, C standing idly by, and then the commutator of A with C, B standing idly by. But A, of course, commutes with itself, so there's only one term, which is an AL commutator with AL dagger. So this is equal to h bar squared over A0 squared mu AL comma AL dagger. And we just worked that one out. And the answer was, it was here. Sorry, I did something wrong? Yes, it's very important. I need an extra factor AL, thank you very much, in the back. This is standing idly by while AL works on his companion. All right, so I now need to plug this in for this commutator, and you can see that all these factors are going to cancel. This factor is going to cancel on this factor, and so we're simply going to get HL plus 1 minus HL times the AL I've been very helpfully told to include. So let me just... Right, so we're now in wonderful shape. So we've completed all 3 steps of the simple harmonic oscillator calculation. And now we just need to go for the point of the exercise, which is so we're given that, we always were given that HL on E and L is equal to E of E and L, right? What we want to do is make ourselves a new, so we've got one stationary state, we want to make ourselves a new stationary state by multiplying by AL, obviously, both sides of the equation. So let me write down the right side of the equation first. This implies that E, which is a boring number, times AL, E and L, is equal to AL, HL of E and L. Usual business. Swap these over. HL, AL, which I'm not entitled to, plus the commutator that restores order on E and L. We just worked that out and found that it was the difference of 2 H's times AL. So this becomes HL plus 1 minus HL with an AL in back. Guess what? We have an HL-AL here with a minus sign and HL-AL here with a plus sign. So the whole thing is equal to HL plus 1 AL, E and L. So we have achieved what we wanted to achieve. That is to say, we have shown that this state is an eigenstate, not of HL, but of HL plus 1, and for the same energy. So the map's looking a little different now from harmonic oscillator, but nonetheless we have a very powerful result. We have generated ourselves from a state which had energy E and angular momentum quantum number L, we've made ourselves a state which can only be characterized as E L plus 1. We've made ourselves a state of the same energy, but more angular momentum. So what have we done? This operator, this is some normalizing constant, right? We had just this kind of thing in the case of the harmonic oscillator. So physically, what have we done? Well, classically, what have we done? We've taken an orbit that might look like this, and we've turned it into an orbit. I'm trying to make an orbit that has about the same semi-major axis and is rounder, if you know about Kepler orbits. So with the same supply of energy, we've increased the angular momentum, so we've made the orbit less eccentric. So in the simple harmonic oscillator case, what did we do? We made ourselves an orbit with less energy, and then we argued that the energy, we're able to show that the energy could never be negative. So we said to ourselves, there must be some... So given this state now, we could apply A L plus 1, A sub L plus 1 to this and make ourselves E comma L plus 2, a state with even more angular momentum. So like in the harmonic oscillator case, we said we can make ourselves an orbit with even less energy. Is this possible with a given supply of energy, with a bound orbit, to have more and more and more angular momentum? No, it's not. At some point, you've got the maximum angular momentum you can have for that given energy, which in classical physics is what we would call a circular orbit. We've completely destroyed the radial motion. See, what we've been doing here is we've been shifting kinetic energy. We've shifted Ke from PR squared over 2 mu to L squared H bar squared over 2 mu r squared, right? This was the tangential kinetic energy. This was the radial kinetic energy. We've shifted energy from here to here. When we've got no energy left in there, or as little as the theory, you know, as quantum mechanics allows, which won't be zero, but will be some amount, then we won't be able to shift any more. So there must be a maximum angular momentum for a given energy. We'll call this curly L, right? This is the maximum angular momentum, and it is a function of energy, but we won't write that it's a function of energy. But we're going to find out what function of energy it is. So what does that mean? That means if we take the, what are we going to call this? The circularization operator, AL, belonging to this maximum angular momentum, and we use it on the state which has the maximum angular momentum for the given energy, what do we get? Nothing. That's the only way we can be prevented from getting a state which has even more angular momentum for the same energy, is if this operator simply kills this state. So we've used this argument twice before, once in the harmonic oscillator case, and also in the case of the angular momentum operators. What do we mean by nothing? What we mean is the mod square of this is nothing. What does that map to? That maps to E, maximum angular momentum, AL dagger, AL, E curly thingy is naught. Where have we seen A dagger A before? I think we must have seen it in the Hamiltonian. We need to replace that by the Hamiltonian times some horrible factors. Yeah. All right, so we already have it here. So A dagger A comes right down to this line here. So this line here can replace the A dagger A in here. So we get to have that E curly L onto A naught squared mu over H bar squared H curly L plus Z squared over 2 curly L plus 1 squared, close a bracket, E curly L, ain't much. But this is an eigenfunction of this operator with eigenvalue E. This is a boring number, so it stands by whilst this bangs into that and makes a 1. This gives me E times this, and this is left over, and it bangs into this and makes a 1. So this implies that A0 squared mu over H bar squared E plus Z squared over 2 L plus 1 squared is nothing, or perhaps I should write this as equals minus. So what have we done? We've got a relationship between the energy and the maximum allowed angular momentum. More than that, we know that these angular momentum quantum numbers, because this is orbital angular momentum we're talking about, we proved that those had to be integers. So n being defined to be is an integer. What integer? We know that curly L is allowed to be nothing, 1, 2, 3, 4. So n is equal to, the numbers it's allowed to be is 1, 2, 3, 4, blah, blah. Nothing not included in the list because of that plus 1. So we have shown that E, the energy, has to be of the form minus Z squared H bar squared over A naught mu. Have I done that right? A naught squared mu. 1 over, no, we need a 2 here, 1 over n squared. So we have found the possible energies of a hydrogen atom. Well, in fact, for a hydrogen like iron, because Z, remember, is this integer which controls the number of charge units on the nucleus, we have found this the possible values, right? It's given by this constant, which we know what it is. We'll simplify it in a moment. We know what it is, times 1 over n squared, where n is 1, 2, 3, 4. So this gives the energy levels. We write this as minus z squared times r over n squared, where curly r is whatever you see it to be, which is h bar squared over 2 a naught squared mu, which is not very intuitive. The way to make this intuitive is to take those a zeros, there are two of them, and turn one of them back into its h bars and things. Now, where did we define a0, for heaven's sake? It was right over here somewhere, right? There it is. So one of those two I'm going to replace by that garbage there, all right? So this is going to become, on the bottom, we're going to have an 8 pi epsilon naught a0. Right, that's the 4 pi epsilon naught. The h bar squared will cancel top and bottom, so that goes away. The mu and the e squared, well, the mu will go away with this, and the e squared will sit on the top. So the Rydberg is what? E squared over 4 pi epsilon naught a0 would be the potential energy of two charges of charge, two electric charges that were separated by a0. So this is half of the potential energy at a separation of a0. And so this is the fundamental energy scale of atoms. And what is it equal to? 13.6 electron volts plus, 13.6 to 3 significant figures. So the energy range at which we work, a battery that you stick into your camera or something has 1.5 volts, basically because of that 13.6 EVs. It's all of condensed matter physics is a mere reflection of that number. Rather, that's why we live at 1 EV, not at 1 MeV or 1 millieV or whatever. So, what do we need to do next? Yeah, jargon. This is called the principal, AL, quantum number. So in these hydrogen-like ions, we've discovered that there are a whole series of distinct states which have the same energy and different angular momenta. So let's talk a bit about degeneracy. Okay, so for principal quantum number n equals 1, we have that L, which is equal to n minus 1, is equal to 0. In other words, the largest angular momentum you can have is nothing. And in the ground state of hydrogen, there's one electron. It sits in the state with the lowest energy, which is going to be associated with n equals 1, and it has no angular momentum. It's on a totally radial orbit in classical physics, right? Not going round and round at all. It just goes in and out, in and out. I mean, in classical physics, quantum mechanics. But it doesn't have any angular momentum. So that's a surprising result. For n equals 2, L is the maximum angular momentum is equal to 1. That means that L can be naught, if you like, and L can be 1, right? This is the maximum angular momentum. So there's a slightly funny thing going on here. N was introduced as 1 plus the maximum angular momentum. But now I'm saying it's better to, what one standardly thinks about it, one thinks about what's the value of n. From it, one takes as n minus 1 the maximum angular momentum. So, and in this sense, we have one state. It'll be two states. Well, this one. Here, basically we have, this is for a spinless particle, right? It'll turn out to be two states when we include the spin of the electron. But remember, we were doing the growth structure, which means we said we were going to forget about the spin of the electron. Here, we would have one state, and here we would have three states, right? Because for L equals 1, we got total angular momentum 1, which means we've got three possible orientations of it. M can be 1, nothing, or -1. So we have three quantum states here, one here. So we've got four states all with the same energy for n equals 2, one for n equals 1, and so it goes down the line. So the number of states is increasing rapidly because there'll be 5 states for n equals 3. The maximum angular momentum will be 2. For 2 units of angular momentum, you've got 5 possible orientations, and then you've still got 3 of these and 1 of those, so that's 9 states, etc. So the structure we've derived is extremely degenerate. What does this have to say about experiments? So stick some hydrogen atoms in a vessel and pass an electric current through and get the electrons knocked out of their comfort zone, and you will get photons coming out at discrete frequencies. Nu is going to be the difference in the energies over h, which is going to be z squared, the Rydberg constant over h not h bar, 1 over n prime squared minus 1 over n squared. This is for n goes to n primed. So if you were in one of these higher states, for example, n equals 2, you will have less, your energy will be a smaller negative number, right? You'll have 1 over 2 squared. You'll have a quarter here, and this will be, if you could then fall down to the state n primed equals 1, in which case this will be 1, so this bracket will be, say, 3/4, and you'll get 3/4 of this number coming out. So that gives you some frequency. And what we have is series of lines, or the way we think about this is that we have a series of lines, each for fixed n primed, i.e. bottom level. So if we fix n primed at 1, we can have transitions from n is 2 to 1, or n is 3 to 1, or n is 4 to 1, and these are the successive lines of the Lyman series. So here we have here is the energy of n equals 1, here's n equals 2, here's n equals 3, and Lyman alpha is the name used for the spectral line associated with an electron tumbling from n equals 2 down to n equals 1, and Lyman beta is associated with from n equals 3 down to n equals 1, which is further to fall, so it emits more energy, so the line appears at higher frequency, shorter wavelength. So the Lyman series is for n primed equals 1. If n equals 2, we're looking at Lyman alpha. That's what it's conventionally called. If n equals 3, it's Lyman beta. And this has, I think it's 112 nanometers. Is that right? 121, sorry. And as you go down to n equals infinity, in other words, if you fall all the way from not being bound into the bottom of the atom, then this is the beginning of the Lyman continuum, and that's, what is it, 92 nanometers, roughly speaking. I've got a more accurate number here, 91.2. So these lines are all in these are all vacuum ultraviolet lines. They all carry, so this one is carrying 13.6 eV of energy, and this is carrying 3/4 of 13.6 eV of energy. So they're carrying enough energy to kick electrons out of the air molecules. So these photons are absorbed by all kinds of things. These are very easily absorbed photons because they carry enough energy to lift electrons out of most atoms. And then we have the next is the Balmer series, which is where the whole story started, which is, so n primed is 2, n equals 3. If you go from 3 to 2, that's called Balmer alpha, but it's written as H alpha because that stands for hydrogen alpha. So Balmer was a Swiss schoolteacher who empirically fitted the formula we've derived. I've lost it. There it is. He fitted that formula empirically to measured frequencies of lines that he identified as being the Balmer series lines. Well, a series of lines which he called a hydrogen series. So this is called H alpha, and it's a pink photon. It's 600 and something nanometers, 656. So it's pink light. So many astronomical objects are pink because they are shining in H alpha, in Balmer alpha. This is H beta, etc. If you then you go to Paschen, that's for n primed is 3, and obviously n can be 4 or 5, etc., etc., etc. So these start off as pink, and they get bluer. So as you go down this list, the wavelengths get shorter as you go to infinity. Where's the series limit? I did write it down here. 364.6 nanometers. So they go from pink light right through the the rest of the optical spectrum to the ultraviolet region. And the Paschen series starts at 1875, I think. So n equals 4, you are looking at 18, yep. So that's already, these are sort of more or less optical. And by now we're in the near infrared, et cetera, et cetera, et cetera. So that's pretty much the right place to stop, I think. What we should do, just one other thing I would point out is that, so you can apply these formulae to the inner electrons to the innermost electrons of other atoms, atoms that have more than one electron. You can't apply them to the outer electrons with any useful way because we've done all this, right, remember, with no other electrons present. We've got one nucleus and one electron. But there's one very important thing to take home, which is that this energy scale goes like z squared. So the characteristic energies of the innermost electrons are going up like z squared. And by the time you get to uranium, which has 92 units of charge, so z is 92, you're almost a factor of 10 to the 4. You're almost a factor of 10,000 higher in energy, which means that these electrons are moving essentially relativistically. So that's just a thing to bear in mind. Okay, and we'll look at the wave functions that go with this lot tomorrow.